I'm Laura Pritchett with the BEAD Core. Let me just keep admitting people into the room, sorry. I wanted to introduce Jamie Perin today. She has a primary appointment in the Department of International Health at the Bloomberg School of Public Health, but we're also lucky to have her as a lead working with the BEAD Core. In case you're not familiar with us, the BEAD Core is the Biostatistics, Epidemiology, and Data Management Core. We provide research support services all over Hopkins, and we are sponsored by the Department of Medicine, Pediatrics, Gyn OB, and the Bayview campus, and soon to be oncology, to provide supported research support services at 20 hours per researcher per fiscal year. So please feel free to reach out to us if you'd like research support services. You can just email beadcore@jhmi.edu and we can talk you through how to access our services. I also wanted to give a brief plug. There will be a survey coming out through Qualtrics by email after Jamie's presentation, and we would really appreciate it if you would take a moment just to fill it out. It's extremely short, and it really helps us with assessing our own seminars, and it gives you a chance to give ideas for your own future seminars that we could provide that would be helpful to you in the future. So if I could just make that plug to please fill out the survey, it would be really helpful for us. So without any, also I wanted to say, if you have questions, please use the chat function. We have found that that works the best. And at the end, Jamie will review all of the questions using the chat function and read them aloud and answer your questions when she's finished, but they will have to wait until the end. So thank you all very much for coming, and let me let Jamie get started. Thank you, Jamie.
Thanks, Laura. Hi, everyone. Thanks for joining. My name's Jamie Perin, and I'm going to be talking about longitudinal data and analyzing longitudinal data. Okay, so just a little about me. My background is in mathematics, and I have a Ph.D. in biostatistics from North Carolina, and I've been working in biostatistics here at Hopkins since 2010. And I started with the BEAD Core in 2012. My very first project was related to the HIV response in Baltimore City. Let me move my window here so we can see the whole slide. Actually, I'm gonna go like this. Okay, that's better. So I'm gonna be talking today, I'm gonna give a very broad introduction to statistical methods for analyzing longitudinal data. And longitudinal data is distinct from many of the analysis methods that we normally use. Univariate statistics are something that we're generally familiar with, where each subject gives rise to a single measurement from a single time point. So I'll be using, so there's lots of vocabulary here, and we're coming from across the schools of medicine and public health. So I'm trying to strike a middle ground for people, because we have so many, our backgrounds are so diverse, but I apologize if the jargon is confusing at any point. So when I say response, that's referring to a measurement that's that we're interested to make some inference about, or that is assumed to have a structural component, but also a random component, and some uncertainty about where it comes from. So univariate statistics are distinct from multivariate statistics, where each person would give rise to more than one measurement that, and those could be things that are measured that mean very different things. For example, we could be measuring pulse as well as respiratory rate, or we could be measuring pulse at different times. And that's the meaning of longitudinal data, when we have measurements that they're the same thing, but they're measured for the same person at different times. So another way to say that would be that we have repeated responses over time on independent units or people. Oh wait, how do I advance my slides? Sorry. Oh. So I'll give some motivation and talk about the advantages and disadvantages of using longitudinal data. And I'll cover some fundamental issues and exploratory analysis with longitudinal data. We'll go through some examples that I've seen over my years of working as a statistician. And then I'll give an introduction for some advanced statistical methods and we're just going to be talking about continuous measurements. So something that could have, or potentially could be located anywhere on a numbered line. We won't be looking at binary data or categorical data. So the methods I'll be talking about, in case any of you are familiar, I'll be covering both marginal models as well as individual level or mixed models. And I'll also briefly talk about transition models that are modeling what's happening now, conditional on what happened in the past. So a longitudinal study is a study where people are measured repeatedly over time, in contrast to a cross-sectional study where a single outcome is measured for each individual. And in longitudinal data, we can investigate both changes over time within individuals, or what might be happening to people as they age or as time passes, as well as the differences among people depending on what's happening at baseline, or what you might call a cohort effect. So in a cross-sectional study, we can compare people based on their factors at a single point in time. But if we have longitudinal data, we can look at their changes over time. Longitudinal data requires special statistical methods because when we have measurements from a single person, they tend to be more similar than measurements from different people. And we generally need to understand how variable our estimates or the things that we measure are, in order to be able to estimate the associations between things that we observe and to determine if those associations are similar to zero, or to perform hypothesis testing. Because if we have measurements that are arising from the same people, then it can be more complicated to estimate that variability. And many times we don't care about what that variability is in itself, but we have to estimate the variability in order to perform hypothesis testing. Another feature of longitudinal data that's not as obvious. I think it wasn't as obvious to me working with longitudinal data, but something I've seen over time, especially in certain applications, is that trends within individuals can sometimes be different than trends across individuals. And we'll see some examples with data later on. So another advantage of longitudinal data is that we have more, there's lots of information that's can be accumulated over time. We have more variability, we have more degrees of freedom, and it can give us more efficiency in the things that we estimate. And also, it gives us the opportunity to resolve causal ordering. You know, instead of, if we had cross-sectional data, we can look at associations. But if we have longitudinal data, we can be more careful about what comes first, as opposed to what is a result. Or, you know, generally, for causal ordering, we would be interested in precedence. And it's not, of course, a perfect situation for making causal inference, but it tends to be more robust than analysis for cross-sectional data. Having longitudinal data also gives us the ability to study the effect of a treatment or a factor on how things are changing over time, rather than what things are at a specific time. And longitudinal data is often, if you're working with a clinical population, it sometimes can be available from extracting clinical records. So it doesn't necessarily require an extreme effort beyond recruiting patients for a cross-sectional study. Or it tends to be that getting additional visits or time for a single person tends to be less work than recruiting an additional person. That isn't always true, but it can be efficient in that sense. So I'm sure that many of you are familiar with linear regression, and I put some formulas up here. Some people like formulas, some people don't. I like to look at formulas. It makes talking about some things a little easier for me. So in our standard linear regression, we have our response y, which we're trying to break down into a structural component or a signal, where we have our x's, which are factors or covariates or things that we think might be influencing our response, and then our betas that are representing the relationship between factors and a response of interest. So we have our structural component in blue here, and then we have a random component or a variance that's in green. And we tend to write that with in this handy equation where we have y equals x beta plus epsilon. So the general assumption for linear regression is, or one of the primary assumptions for linear regression, is that these error components across records or observations are independent of each other. And if we have different people, that's usually a very reasonable assumption. But when we have longitudinal data, then that assumption that those measurements are independent is no longer reasonable. And in almost every case, we can't assume that. And we need that assumption in order to estimate how variable our regression coefficients are, and to make good tests of our associations and to understand our response. We need good estimates of the variability. So instead of, when trying to represent longitudinal data, I've included another. So before we only had yi, And now we have 2 indexes on each response, which is representing both the person that the measurement is generated from and the time that the measurement was recorded. So for subject I at time J, we have this representation of an outcome that we would like to describe and examine associations for. But in order to do that well, we have to account for this relationship between the random variation for the same person. We can still make the assumption that random errors for different people are independent, but we will no longer assume that when they're from the same person that they aren't related. So for our standard linear regression, we could have this where we assume a normal distribution with independent errors, and we can make that same assumption about normality, but now we're assuming this, we're accounting for a correlation between the noise and their longitudinal, the motivation for longitudinal data analysis is to let the data be correlated with in person and to make an estimate of that correlation. And there's lots of different ways of doing that, but that's the additional primary target of longitudinal data analysis compared to a standard linear regression. So here's an example. This is child BMI that is standardized by age and gender. And just looking at this, so I've been working with this data, but from your perspective, I mean, this could be, cross-sectional data, or it's not clear how these things are related. But this is a starting point for these data that were measured over time for children in Baltimore City. And this is data I've been working with a pediatrician, Rachel Thornton, who some of you may know. So one of the questions here was whether the standardized BMI was changing over time. And so we could look at a general trend. This is just looking at the average over time, which doesn't appear to be changing a lot. But we could also look at the trends within individuals. So this here is showing connecting measurements that were from the same child. So there's a possibility both. So we have our population trend and the overall average, but we also have potentially different trends within individuals. So this is actually not real data, but this is some data that was made up to illustrate a point. But I mean, this is something, so in this example, we have, we're looking at the child reading ability, however that's measured, compared to age. We would expect that to be increasing with age, although maybe under lockdown, that's not exactly happening. But we could also, this might be, so we can observe here the trend across the population, but there's also potentially a trend within individuals. So that trend if people are being measured, if children are being measured over time, that trend, it could be both at the population level, it could be similar, what's happening within individuals, but it's also possible, depending on reading ability is, because that's due to the complexity of that, and with most things that we observe for people. It's also possible that here we see, just given how people are connected, that the trend within individual could be contrary to the trend across individuals. And there could have been, a secular event, or some bad kindergarten experiences, for example, that would cause something like this. And this isn't real data here, so it's hard to understand exactly, but I have seen this in real data, and they weren't as nice examples to talk about. But the within individual trends can be different to the trend across individuals. And sometimes, this here being in the opposite direction. And so if you had been looking at this cross-sectionally, this is something you would completely miss. So we have repeated observations, which are likely to be correlated and violating our assumption of independence, which is necessary for most statistical analysis. And so if we used standard regression methods, and you wouldn't think this would be very common, that longitudinal data is appreciated in most areas enough that people would be careful, but I actually have seen it published where it's been ignored and like linear regression is used. So in that case, the correlation, because you're assuming that it's zero, so that will be biased. And in the event that the correlation is of scientific interest, which in some cases it might be, we wouldn't be able to make any exploration of that. In addition, we would have our estimates of beta, because we wouldn't get good estimates or accurate estimates of that variability. Our estimates of beta would be inefficient. As well, our standard error estimates for beta would be too small. So we would find when standard errors are too small, we would be more likely to find a significant association than our stated type 1 error, which is would be an anti-conservative trend, which is generally not very well accepted. So we don't want to be anti-conservative. We don't want to increase our type 1 error. But in order to do that, we need longitudinal data analysis. So we have lots of opportunities with longitudinal data. We can estimate effects at different levels. We can look at different targets for our estimation. And we have the range of research questions that we can address is more broad. But in part because there's more data and because of the wider possibility for research questions, there are more choices involved. And one of those things is choosing a timescale. In thinking about the child BMI, we have one very important timescale, which is age, which in that case, there was a research question around age. So it was a natural timescale to pick. But there's also, there might be a secular trend in BMI. So that is an alternate timescale. We also have we have this correlation, and so between outcomes for the same person, and we need to have some understanding of what that is so we can model it, which is an additional challenge of analyzing longitudinal data. However, I would say that the biggest challenge to working with longitudinal data is that if you're following people over time, or even if you're putting together clinical records that are retrospective, some people, they tend to be lost. And if you enroll someone just for a single time point, then you have everything there when you enroll them. But if you're following them over time, then people move away. People change their minds about being in the study, or some people, they might change clinics. And it can be a challenge to understand why that happens and the implications for analysis. There are good methods to explore that, though, so it's not an insurmountable challenge. But there's always something to keep in mind when you're working with longitudinal data. So we talked here about missingness. One of the other challenges for longitudinal data analysis is diagnostics, because diagnostics for standard or for approaches with cross-sectional data are very well developed, especially for linear regression. And even though there are diagnostics for longitudinal data, they don't tend to be in as wide use, and so they aren't as user-friendly and they aren't as standardized. It can also be more difficult to think about correlations and to have an intuitive feel for what they mean and how well they fit. If you're fond of eyeballing data, then correlations are more difficult than means to eyeball in most cases, and for most people. So I'm talking too much, I suppose. I'm going to go through this quickly. So it can be nice with any data, really, but especially with longitudinal data, to look at things in an exploratory way, just to get a feel for what's happening. And you might have your very pre-specified analysis plan, but then aside from that, you would probably be looking at your data in an exploratory way to think about other research questions and to double check what you had planned for your analysis. So scatter plots are always useful. It can be a good way to get a feel for what's happening overall. Oops. We can also look at spaghetti plots, what we saw, where each individual's measurements are connected with a line. And we can also look at the average and distributions at each measurement time using box plots and quantiles. And given that, we could look at means and medians and how variable things are. People also tend to look at empirical covariances, which can be helpful if you're thinking about a model for your correlations. So just to get a starting point and make sure that you're picking the most appropriate thing. And people also look at something called a Paris plot. I'm not sure I have an example of that here, but that would be, it's like many different scatter plots of things at where each pair is at different times. And it also can be helpful to use, we could do a smoothing over time, like we saw for the child BMI, to highlight a typical response or how things are changing overall. So I have some examples here, mostly in the biomedical realm. I'll be talking about a CD4 count, as well as epileptic seizure rate, and also about the protein contents of milk in an agricultural study. So in this CD4 example, and I'm not an HIV expert, so I apologize if I speak loosely about these data, but we have where HIV attacks CD4, which regulates immunoresponse, and we had over 2,000 measurements of CD4, and as well as a time of seroconversion for a group of individuals enrolled in the MAX study from Baltimore City. And this is, I want to say this was 2003, but the question was that what is the impact of HIV infection on CD4 counts over time? Oops. So the goals were to characterize the typical time course of how CD4 count was declining in individuals, and to identify factors which could predict the changes in CD4 count, as well as estimating the average trend of CD4 decline or change over time, and to characterize how the degree of heterogeneity or how different men tended to be in the rate of CD4 change. So we have here, so we have a scatter plot of the CD4 count compared to time since seroconversion. And this just shows, so because we have so much data here, it can be hard to appreciate. I mean, really what we'd like to see is the change for each person in the study, for each man in the study. But it's hard to represent them all at once because there's so many, and because CD4 was measured so many times. But sometimes it can be helpful to look at just a few individuals or to look at them in groups so that we can appreciate and still see what's happening overall. It's hard to see, but there's a dotted line that's the overall trend that we can see that that's in decline. It starts around 1,000 and then it ends up over here around 500. But then, and that is a very smooth line because we're taking this average over all people. But then for each individual, that CD4 count is it's bouncing around a lot, so it's quite noisy. And this is why, so it's a spaghetti plot and it's not very pretty. And if you have a bunch of data, then it can be hard to look at these because it's easy to pick out the spikes, and those seem to be around the time of seroconversion. But then it's, so we can sort of pick out that there is a general decline, but then is that just in these extreme values or is it overall? So this by itself is one of the standard things that people look at with longitudinal data. But if your measurements are noisy and CD4 count is, then it can be a challenge. And this by itself probably isn't enough. Or there's more to this data than can be represented in a spaghetti plot. So we could look just at individuals. We could look at trends based on for people based on their baseline age or race or socioeconomic status or other things that were happening for them when they entered the study. So this is a little easier to look at than our full spaghetti plots, but then not everyone is represented here. So another thing, so this here is an empirical correlation matrix. And so in our standard linear regression, you'd have ones on the diagonal here, and then we would have zeros everywhere else. And I look at correlation matrices a lot, so I apologize if there's probably things here that I'm not pointing out very well. And one of the things is the dimension. So correlation matrices are that each entry in that matrix is a correlation between two variables. And here it happens to be CD4 count that's measured at different times. So if we look at the 0.8 in our second row, first column, that's the correlation between the first measured CD4 count and the second measured CD4 count. I included this because it's very common to examine correlation matrices to get a feel for what the best analytic methods would be. But also, many things that are measured over time, especially in this instance where they're measured up to 12 times for individuals, they tend to be, if they're measured closely in time, they tend to be very strongly related, but that might tend to decay. So your first CD4 count, or the correlation between the first CD4 count and the last CD4 count, is actually in this, the bottom left corner, which is, it's very small. Here's a correlation matrix for our child BMI, and we had fewer measurements for them, but the correlations also, they tended to be stronger and to be maintained over time, which, if you work, because the BMIs were standard across age, so it's more, this wasn't surprising to me. If you work with BMI, it might not be. So we also have, we're running a little short on time, so I think I might skip our next examples. So these examples, they all had repeated observations on experimental units where the units can be assumed independent, but where multiple responses for each unit or person are likely to be correlated. And we can formulate our objectives as regression problems whose purpose is to describe the dependence of a response on explanatory factors. So if we only have one observation, we're very limited, and we would mostly be looking at averages, or population averages. But if we have repeated measurements, we can, so one of the standard things that is done is it's possible we could take those things that are repeated over time and reduce them into a single measurement for each independent thing or each person. So we would make a summary and then analyze that summary as in relation to some group of covariates. So it would be like having two-stage analysis. So if we had a seizure rate measured at different times, we could look at an average seizure rate across the whole study period and then compare rates for two arms, for example. if we had something that wasn't changing over time. We could also look at a trend. We could say, instead of having an average seizure rate, we could summarize that to say seizure rate was increasing or decreasing over time. So some more sophisticated methods to analyze longitudinal data. One of the main things in this statistical language, people tend to refer to it as the marginal model, where we model the variance or that correlation of the response directly. And one of the ways to do this is with generalized estimating equations, which some of you may be familiar with. We could also, so the second class of models would be our random effects, where we let our responses be correlated by giving them common effects, represented here by this U. Another common method that is used is, I've called them transition models, where we look at the average at the current time and conditional on what's happened in the past. So comparing marginal models with standard linear regression, we could specify a mean model in the same way as we would, or a similar way, for if we had linear regression for cross-sectional data, where our coefficients describe and compare subpopulations. And the regression coefficients are representations of associations between our response and covariates. And then we have a second model for the correlation, which is specified separately. For our random effects models, we still have this regression coefficient core that's similar to the linear regression, but then we have an extra level that is specific to each independent person or thing. So it's similar to each person in your study having their own intercept, where the regression coefficient is common across people, but the intercept is no longer common across people. And this, due to some statistical properties, the regression coefficient is no longer, it's interpretable at an individual level and not the population level. So in transition models, so our prior responses would be like predictors of our current response. And they're potentially complex, especially if there are many times where folks are being measured. And for that reason, and others, they're probably less common. One of the instances where I see this a lot is where people are only measured at 2 times. And then you might have, you could look at a change, or you could look at current, based on the past, but there's less choices because there's only one thing in the past there. And especially where a dropout is not a concern, because in that case, in contrast to marginal models and random effects models, if someone doesn't have both of these, both past and present, then they can't contribute, which can be a bad thing. So which method of these is best is often guided by the primary research question or by the type of measurements and what data are available. One of the strong statistical standards is that when dropout is a concern, or when it's level is high, that random effects models are usually preferred. And transitional models are not recommended for responses that are unevenly spaced in time. This can, choosing a method can be, there's more methods for longitudinal data than, or they tend to represent, the variety is quite intense compared to what's available for cross-sectional data. So it's not a bad idea to reach out for help to the BEAD Core or to the ICTR. So I'll go through this quickly. We're getting close to time, but so for our example with the CD4 counts, we had thousands of measurements for 300 odd people, 300 odd men in the MAX study. So I fit them with an exchangeable correlation, which, and you could argue if that's the best or not. That assumes that correlation was similar over time. And then estimated just the change in time, or how time is associated with the change in CD4 count. And so for our parameters, we have that beta naught is the population average CD4 count at the time of seroconversion. And then our beta 1 is the change in CD4 count for each year thereafter. And we get an additional estimate of how strongly related those CD4 counts are, our correlation at 0.5, which that measure can range from -1 to 1, and 0.5 is quite strong for individual level data, for people data. When we fit a random effects model, it just worked out that our parameter estimates are very similar. This is often not true. And then we get this, the other thing that we estimate as part of this is the variability of that person level effect. So it can be nice just to compare, we can benchmark that against our average CD4 count at baseline. So the population, or generally people tend to be around the mid 800s, but many people start outside that. Within 250 cells, plus or minus from the mid 800s, you would get approximately a third or 2/3 of your data. So I did not fit a transitional model for the CD4 count because it's unevenly spaced and because there are so many measurements. So that would not be recommended for this case. So our time is about up. I wanted to include some public tutorials. There's lots of software that's available for analyzing longitudinal data. I know people are using lots of different things. There's some really great things out there for Stata. R tends to be, when there's new methods that come out for longitudinal data, R tends to have them first, but it doesn't take long for Stata and for other software packages as well to make those available. And that's it. Thank you. I wanted to thank Francesca Dominici because I borrowed from her slides on longitudinal data, and also to the departments of pediatrics, medicine, and OB/GYN, and the Bayview campus for supporting BEAD Core. Let's see. Now, I have not been paying attention to, how do I go back to?
Can you see the chat, Jamie? The first question that I see is, how exactly did you choose the correlation between the time points?
Oh, the correlation between the time points. I assume you're talking about the CD4 analysis. So generally, in order to pick a correlation structure, I would look at an empirical covariance, which we saw that blue thing up here. So I looked at this, and so an exchangeable is one of the more common ones. So and that assumes that that this correlation is consistent over time. And we can see there's a delay here. So you could also use an autoregressive. So there's different, there's a handful of correlation structures that are used mostly. And so I looked at the correlation, this empirical correlation, but also just if you understand your response and how you expect that. So this is a lot of things decay over time, that would be an autoregressive structure. And an exchangeable it can be, sometimes if you have structures that are very complex, those can be more difficult to fit, and you can have convergence problems depending on your data. So the exchangeable is like the sort of, if you can't fit anything else, you can almost always fit the exchangeable. So sometimes that's like a next best. I hope that's helpful.
Jamie, do you want me to keep reading the questions, or can you see them?
I'm sorry, I can't see them.
I'm happy to help. There. The next question I see is, should a marginal model be used for an RCT, and what are the guidelines?
That's a good question. Many times, whether people use marginal or mixed or transition models, it's based on what people have done previously. And there are certain studies, certain RCTs where people just tend to use marginal models. And especially, so I've used it, and particularly if you don't have a lot of dropout, you can almost always use marginal models if you can answer the questions that you're interested in, if it's for an RCT or for observational data. And there's lots of precedent for that across different fields. When dropout is more than an acceptable level, and where that level is exactly can be different in different areas. Sometimes 10% isn't considered a lot, although if you're following a certain population, if that's more than is expected, then you might want to consider something other than marginal models. But in general, I would say marginal models are very acceptable for RCTs.
I have another question here for you, Jamie. Can a random effect model give you an R-squared the same way as in linear regression?
That's another good question. So I think there are several statistics that have been defined that are like the analog of R-squared for cross-sectional models, but none of them are very widely used. And I'm not very familiar with them because I should be more familiar with them. But because there's several, there's really not a standard in that area. That might be an active research area, but there's not something that that's in standard usage right now that I'm aware of. And that's one of the challenges, because there's less guidance on the statistical front about how to choose the best model and how to understand models when you're working with longitudinal data, because something like in R-squared, there's just not a lot of convention around what to use there. Were there any other questions, Laura?
I don't see any more. Does anyone else have any other questions they'd like to? Please type it in the chat if so. And Jamie, I forgot to ask you, will we be making the slides available? Is that all right?
Sure, of course.
Okay. Anyone who would like a copy of the slides, please email beadcore@jhmi.edu and we will send them to you. You're getting a lot of thanks and thank yous in the chat, Jamie, so I don't see any more questions.
Thank you so much, everyone, for listening.
Thank you so much for your time, Jamie. That was really interesting and helpful. Thank you so much. And everyone, please make sure you fill out the survey that we send along, and we appreciate your time today. Thanks again.
Thanks, Laura.